Tonight, we're going to talk about something that should keep you awake at night. A question so simple a child could ask it, but so profound that the world's greatest minds still can't answer it. Where is everybody? We live in a universe with 200 billion trillion stars, most of them with planets. Many of those planets potentially habitable, and the universe has had 13.8 billion years to fill up with life. So where are they? Why haven't we heard a single signal, seen a single sign, detected even the faintest trace of another civilization anywhere in the cosmos? This isn't just an interesting question. It's a paradox that strikes at the heart of everything we think we know about our place in the universe. And by the end of tonight, you're going to understand why this silence is one of the most disturbing mysteries in all of science, and why every answer we come up with only makes the question more unsettling. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. In the summer of 1950, Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory. Fermi was one of the most brilliant physicists of the 20th century, the kind of scientist who could solve problems in his head that other people needed computers for. He'd helped build the first nuclear reactor, worked on the Manhattan Project, won the Nobel Prize. That day at lunch, the conversation had turned to flying saucers. This was the height of the UFO craze. Newspapers full of little green men and alien spacecraft. The scientists were joking around, light-hearted banter about visitors from other worlds. Then, Fermi went quiet. When he spoke again, he asked a question that seemed to come out of nowhere. Where is everybody? His colleagues knew immediately what he meant. Nobody had an answer. Nobody has a good answer now, 76 years later. We've been looking. We've pointed radio telescopes at the stars, listening for signals. We've scanned millions of stars across thousands of frequency channels. We've studied thousands of planets orbiting other suns. We've searched for megastructures, for signs of engineering, for anything that couldn't be explained by natural processes. And we've found nothing. Not one confirmed signal, not one artificial structure, not even the faintest trace that anyone else is out there. The silence is absolute. Now, you might think, well, space is big. Maybe we just haven't looked hard enough. But here's the thing that makes this truly disturbing. If intelligent life were even remotely common in the universe, we shouldn't have to look hard at all. We should be drowning in evidence. We've now confirmed over 5,000 planets orbiting other stars. Planets aren't rare. They're everywhere. Almost every star has at least one planet. The Milky Way probably contains somewhere between 100 billion and 400 billion planets. And a significant fraction of those are rocky worlds in the habitable zone, places where liquid water could exist, where temperatures are moderate, where life could arise. That's tens of billions of potentially habitable worlds just in our galaxy. And the universe has had time. Our sun is only 4.6 billion years old. The universe is 13.8 billion years old. Stars were forming and hosting planets for 9 billion years before Earth even existed. If life arose on any of those older worlds, at roughly the same pace it arose here, there could be civilizations out there that are billions of years older than us. Think about what humans have accomplished in just 250 years of industrial civilization. We went from steam engines to nuclear reactors, from the telegraph to the internet, from wondering if we could fly to landing on the moon in just 66 years. Now, imagine a civilization with a million-year head start, or 1 billion years. What would they have built? A civilization just a few thousand years more advanced than us could harness all the energy of their star. You build a shell or swarm of collectors around the star to capture all its output. This is called a Dyson sphere. It sounds impossible, but it's just engineering. You disassemble planets for materials, use advanced robotics and construction techniques. There's nothing in the laws of physics that says you can't do it. And here's the crucial part. We could see it. A Dyson sphere would block the star's visible light and radiate heat in the infrared. We've scanned thousands of nearby stars, specifically looking for this signature. We've found nothing. Even without megastructures, we should see signs of expansion. You don't need faster than light travel to colonize the galaxy. Build a ship that travels at 5% of light speed, which is ambitious but achievable. At that speed, it takes about 80 years to reach the nearest star. The ship arrives, builds infrastructure, constructs more spacecraft. Those spacecraft launch toward other systems. One colony becomes two becomes 4. This is exponential expansion. How long to colonize the entire galaxy this way? Between 5 million and 50 million years. The Milky Way is 13 billion years old. 5 million years is less than 0.1% of the galaxy's age. If any civilization anywhere had developed interstellar travel even 100 million years ago, they should be everywhere by now. Every star system, every habitable planet. We should see their probes, detect their signals, find their artifacts. But we don't. Just silence. This is the Fermi Paradox. The universe appears to have everything needed for life. Billions of habitable planets, billions of years, for civilizations to arise and spread. But they're not here. Or if they are, they're hiding so well that we can't detect even the faintest trace. So where is everybody? There are only a few possible answers, and none of them are comforting. The first possibility is that we're alone. Life is extraordinarily rare, requiring such a specific, unlikely combination of circumstances that it's only happened once, here on Earth. All those billions of potentially habitable planets might be empty, dead worlds with rocks and water but no life. Think about what had to happen for life to arise on Earth. 4.5 billion years ago, Earth formed from a disk of dust and gas orbiting the young sun. Initially, it was a ball of molten rock, bombarded constantly by asteroids and comets. The surface was liquid magma, the atmosphere toxic, temperatures hellish. For hundreds of millions of years, Earth was completely uninhabitable. Gradually, the bombardment slowed, the surface cooled and solidified, water vapor condensed and rained down, forming the oceans. Somewhere in this early Earth, probably in the oceans, chemistry became biology. Non-living molecules organized themselves into something that could reproduce, metabolize energy, evolve. We don't know how this happened. This is one of the biggest unsolved questions in science: the origin of life. The oldest evidence of life on Earth dates back about 3.8 billion years. Earth was only about 700 million years old when life appeared. That suggests that once conditions were right, life arose fairly quickly. But does that mean life is easy? Or that we got incredibly lucky? We've never observed life arising from non-life. We've synthesized complex organic molecules in laboratories, amino acids and nucleotides, the building blocks of proteins and DNA. The famous Miller-Urey experiment in 1953 showed you could create amino acids by running electricity through gases similar to early Earth's atmosphere. But that's still a long way from life. Life requires metabolism, the ability to extract energy from the environment. It requires reproduction, the ability to make copies. It requires heredity, the ability to pass information to the next generation with occasional variations that evolution can act upon. Getting all of that from chemistry might be incredibly rare, happening only once in a trillion planets. If simple life is rare, complex life might be even rarer. Earth had single-celled organisms for about 3 billion years before anything more complex evolved. For that entire time, life existed, but it was all microscopic, all single-celled. Then, about 2.1 billion years ago, something remarkable happened. One cell engulfed another cell, but instead of digesting it, the two cells merged. The smaller cell became the mitochondria, the powerhouse that provides energy to complex cells. This is called endosymbiosis, and it appears to have happened exactly once in Earth's history. Every complex organism on Earth, every plant, every animal, descended from that single merger event. It never happened again. Why? We don't know. Maybe it's incredibly unlikely, requiring conditions to be exactly right. If endosymbiosis only happens once per planet per several billion years, then most planets with life will be stuck at the single-celled stage. They'll have bacteria, maybe algae, but nothing more complex. Then you need multicellular life, which happened about 600 million years ago. Single cells started sticking together, forming colonies, then differentiating into specialized cell types. Some cells became dedicated to gathering food, others to reproduction, others to structure and support. This required incredible coordination. Cells communicating with each other, regulating their growth, suppressing their individual reproduction for the good of the organism. This took billions of years to happen. Once you have multicellular life, you need complex animals with brains and nervous systems. That happened during the Cambrian explosion, about 540 million years ago. In a relatively short period, geologically speaking, most of the major animal groups we see today appeared in the fossil record. But notice the timeline. Life arose 3.8 billion years ago. Complex animals appeared 540 million years ago. That's a gap of over 3 billion years. Earth spent most of its history with life, but no animals. Then you need intelligence. Not just brains, but complex brains capable of abstract thought, language, tool use, culture. On Earth, this level of intelligence has evolved exactly once, in our lineage, in the last few million years. Lots of animals are smart. Dolphins, elephants, crows, octopuses. But none of them have developed technology, built cities, asked questions about the cosmos. Just us. Why? Partly it's our hands. We can manipulate objects with precision, make and use complex tools. But lots of animals have grasping appendages. Raccoons have dexterous hands. They don't build civilizations. Partly, it's our social nature. We live in large groups, cooperate, share knowledge. But lots of animals are social. Ants and bees have incredibly complex social structures. They don't develop technology. Partly, it's our big brains. Humans have brains that are disproportionately large for our body size, consuming about 20% of our total energy, while making up only 2% of our body weight. That's expensive. There must have been strong evolutionary pressure to develop such costly organs. But what pressure, exactly? We don't fully know. There are theories about climate change, forcing our ancestors to adapt quickly, about the advantages of hunting in groups, requiring better communication, about sexual selection, where intelligence itself became attractive to potential mates. But the honest answer is, we don't completely understand why humans became so smart. And if we don't understand our own evolution, we can't predict whether it would happen elsewhere. Maybe the combination of factors that led to human intelligence is so specific, so unlikely, that it happens on only one planet in a billion. Earth has also had several major transitions in its history, where life had to adapt dramatically. The most famous involved the dinosaurs 65 million years ago, probably caused by an asteroid impact. But there were others, more dramatic ones. The Permian-Triassic event, 252 million years ago, affected the vast majority of species on the planet. It was one of the most significant resets in Earth's biological history. What caused it? Probably a combination of factors: massive volcanic eruptions, climate shifts, ocean chemistry changes. The point is, life is both resilient and vulnerable. A planet can support complex life for hundreds of millions of years, and then conditions can change dramatically. If Earth's history had gone differently, if certain transitions had been more or less severe, the path to intelligence might have taken a different route or not happened at all. We're here because the timeline worked out favorably. The rare Earth hypothesis says that luck is rare. Most planets don't have all the factors lined up correctly, and we're the one planet where everything went right. If that's true, then we're alone, and the silence makes perfect sense. The second possibility is much worse. Maybe civilizations are common. Maybe life arises on millions of planets. Maybe intelligence evolves regularly. But maybe civilizations don't last. Maybe they destroy themselves before they become visible. This is called the Great Filter. The idea is that there's some step in the development from chemistry to spacefaring civilization that's incredibly difficult to pass. A filter that most attempts don't make it through. If it's in the past, behind us, then we've already passed it, and the hard part is over. Maybe the filter is the origin of life itself, or the jump to multicellular organisms, or the evolution of intelligence. If any of these steps is incredibly difficult, rare enough that it only happens once per galaxy or less, then we've passed the filter, and the universe ahead of us is wide open. But there's another possibility, and it's terrifying. What if the filter is ahead of us? What if the hard part isn't the origin of life, or the evolution of intelligence, but surviving your own technology? Think about where we are right now as a civilization. We've developed technologies that would seem like magic to someone from just a century ago. We can communicate instantly across the entire planet. We can see inside living cells and watch atoms move. We've sent robots to other worlds and brought back pieces of the moon. We've decoded the human genome and learned to edit DNA. We're building machines that can learn and think in ways we're only beginning to understand. And we're doing all of this in what amounts to the blink of an eye, in cosmic terms. Here's what's fascinating about this. Technology doesn't advance steadily, it accelerates. 100 years ago, the fastest way to cross an ocean was by steamship, taking weeks. Now we can fly anywhere on Earth in less than a day. 50 years ago, the most powerful computers filled entire rooms and had less processing power than a modern phone. Our capabilities are growing exponentially, and we're living through one of the most rapid periods of change in human history. The question is, what happens next? Do civilizations that reach this level of technological advancement tend to keep growing, spreading out into space? becoming truly interstellar? Or is there something about this stage, this moment of rapid acceleration, that presents challenges most species struggle to navigate? And the problem compounds over time. Every new technology creates new risks. Every advance in one field enables advances in others. Biotechnology gets cheaper and more accessible every year. Artificial intelligence gets more capable. The tools to create catastrophe become easier to obtain, easier to use, easier to misuse. This isn't about any one country or any one threat. It's about the challenge every technological civilization faces. How do you survive your own inventions? How do you develop the wisdom to match your power before your power destroys you? It's like giving a child the keys to a car before they're old enough to understand the consequences of driving recklessly. Except the car is civilization, and the consequences are extinction. We're navigating this period right now, the dangerous century, some scientists call it. The time when we have world-ending capabilities, but haven't yet developed the global coordination and long-term thinking needed to prevent their use. Most of human history, our biggest threats were natural: disease, famine, predators, natural disasters. Now our biggest threats are ourselves, the things we've created. And unlike natural threats, which we've learned to predict and prepare for, these technological threats are new. We're figuring out how to handle them in real time, making up the rules as we go. The question isn't whether we can build dangerous things. We clearly can. The question is whether we can build the political systems, the social structures, the shared values needed to prevent those dangerous things from being used. Can we cooperate globally when threats are global? Can we think long-term when our institutions are designed for short-term problems? Can we restrain ourselves from using technologies just because we can, when using them might destroy everything? These aren't theoretical questions. They're the test every technological civilization must pass. And the silence from the galaxy suggests that most civilizations fail this test. We have artificial intelligence advancing rapidly, and nobody really knows what happens when AI becomes smarter than humans. Right now, AI can beat humans at chess, at Go, at complex video games. It can generate coherent text, create realistic images, write code, diagnose diseases. But current AI is narrow, specialized for specific tasks. It doesn't have general intelligence, the ability to reason across domains, to set its own goals, to improve itself. That might change. Many researchers believe we could develop artificial general intelligence, AGI, within decades. Once we have AGI, it could potentially improve its own code, becoming more intelligent, which allows it to improve itself further, leading to an intelligence explosion. The concern isn't that AI will become evil, it's that AI will be indifferent. If an AGI's goals aren't perfectly aligned with human values, it might pursue those goals in ways that are catastrophic for us. The classic thought experiment is the paperclip maximizer, an AI designed to make paperclips that become so good at its job it converts all available matter, including humans, into paperclips. It's not hostile, it's just optimizing for the wrong thing. We have climate change, altering our planet faster than ecosystems can adapt. Carbon dioxide levels in the atmosphere are higher than they've been in millions of years. Global temperatures are rising, ice sheets are melting, sea levels are increasing, weather patterns are becoming more extreme. We know this is happening, we know we're causing it, and we're not stopping. We're reducing emissions too slowly to avoid significant warming. The consequences will be severe: coastal flooding, agricultural disruption, water shortages, mass migration, conflict over resources. These might not end civilization, but they could severely weaken it, making us more vulnerable to other threats. We have all these existential risks, and we're still figuring out how to deal with them. We don't have a world government that can coordinate global responses to global threats. We have nation-states, many of them hostile to each other, all pursuing their own interests. We have short political cycles, where leaders focus on the next election, not the next century. We have economic systems that prioritize growth over sustainability, profit over long-term survival. And we're introducing powerful technologies faster than we're developing the frameworks to manage them safely. Maybe that's the filter. Maybe every civilization reaches this point, where they develop the power to destroy themselves, but not yet the wisdom to avoid doing so. And maybe most civilizations fail. They blow themselves up in nuclear war, engineer a pandemic they can't control, create an AI that decides humans are unnecessary, wreck their planet's climate beyond recovery. There are many ways a technological civilization could stumble. Here's the challenging part. We need to get things right consistently. A major catastrophe only needs to happen once to set everything back. We need to succeed repeatedly over centuries, while the risks only need to materialize once. It's an asymmetric challenge. If the great filter is ahead of us, if most civilizations don't make it past their technological adolescence, then the silence makes perfect sense. The galaxy might have been full of civilizations, hundreds or thousands of them, all asking where is everybody, just like we are. And then, one by one, they faded. They reached a point where their technology outpaced their wisdom, and they couldn't navigate the challenges that came with it. They lasted a few hundred years, maybe 1,000, after developing radio and spaceflight. And then the signals stopped. This interpretation of the Great Filter suggests that the next few centuries are critical in human history. This is our test. Can we develop the political, social, and ethical frameworks to handle our technology safely? Can we be wiser than those who might have come before us? Can we be the exception? The silence suggests it's difficult. But someone has to be first. Maybe it's us, or maybe we're just the latest to ask the question, and in time, another civilization will look up at the stars, ask where is everybody, and not know that we were here, briefly wondering the same thing. The third possibility is equally disturbing, but in a different way. Maybe the galaxy is full of civilizations, but they're all hiding, staying quiet on purpose, because revealing yourself is dangerous. This is called the dark forest hypothesis, named after a science fiction novel by Chinese author Liu Cixin. Imagine the universe as a dark forest at night. You're alone in the forest, or at least you think you are. You can't see very far. You know that predators might be out there, but you don't know where. Do you light a fire to keep warm and cook your food? Or do you stay dark and quiet because a fire would reveal your location to anything looking for prey? That's the dilemma facing every civilization. The logic goes like this. Resources in the universe are finite. Any expanding civilization will eventually need more resources, more energy, more space. If two civilizations encounter each other, they have three options: cooperate, compete, or one destroys the other. Cooperation requires trust. But you can't trust an alien civilization because you don't know anything about them. You don't know their psychology, their motivations, their capabilities, their intentions. They might be friendly, they might want to trade and share knowledge, or they might see you as a threat to be eliminated or a resource to be exploited. You can't know which, and they can't know whether you're trustworthy either. This is a coordination problem, and it's made worse by the speed of light. Communication across interstellar distances takes years or decades or centuries. By the time you receive a message from another civilization and send a response and receive their reply, decades have passed. In that time, their capabilities might have changed dramatically. The friendly civilization you contacted might have been taken over by a hostile faction, or they might have developed new weapons you don't know about. Or they might have decided you're a threat after all. The speed of light doesn't just make communication slow, it makes trust impossible. Because even if you trust them now, you don't know what they'll be like in 50 years, when your message reaches them and their reply reaches you. There's another problem: the chain of suspicion. Even if you think they're friendly, you can't be sure they think you're friendly. And even if they think you're friendly, they can't be sure you think they're friendly. Each side is thinking not just about whether the other is a threat, but about whether the other thinks they're a threat, and whether they might attack preemptively because they think you might attack preemptively. This is similar to the security dilemma in international relations. Even if both sides want peace, the lack of trust can lead to an arms race or even war, because each side is preparing to defend itself against the possibility that the other side might attack. In the dark forest scenario, this logic leads to a grim conclusion. The safest strategy is to destroy any other civilization you detect before they become powerful enough to threaten you. Not because you're evil or warlike, but because you can't take the risk that they might destroy you first. It's a preemptive strike driven by fear and uncertainty, not malice. If every civilization follows this logic, then the universe becomes a very dangerous place. Any civilization that reveals itself becomes a target. The first one to broadcast their location is the first one destroyed. So everyone stays quiet, everyone hides, everyone listens, but no one speaks. The galaxy is full of civilizations, but they're all terrified of each other, all hiding in the dark, all alone. This would explain the Fermi Paradox perfectly. No radio signals, because broadcasting is suicide. No Dyson spheres or megastructures, because they would be too visible. No expansion, because colonizing new star systems would leave a trail that could be traced back to your homeworld. Just silence and isolation, every civilization huddled around its own star, trying desperately not to be noticed. If this is true, then our SETI broadcasts might have been a terrible mistake. We've been beaming messages into space for decades, announcing our presence to anyone who's listening. In 1974, astronomers used the Arecibo radio telescope to send a message toward the globular cluster Messier 13, 25,000 light-years away. The message contained information about Earth, about humanity, about where we are in the galaxy. We thought we were reaching out in friendship. But if the dark forest hypothesis is correct, we might have just painted a target on ourselves. Some scientists have argued strongly against METI, messaging to extraterrestrial intelligence. They say we shouldn't be broadcasting at all until we know more about what's out there. Others argue that we've already revealed ourselves. Our radio and television broadcasts have been leaking into space for over a century. They're weak signals, they degrade over distance, but they're out there. Anyone within about 100 light-years with sensitive enough equipment could detect them. We can't take it back. The message is already sent. If someone out there is listening, and they mean us harm, they already know we're here. The dark forest hypothesis is paranoid, but is it wrong? Human history suggests that when a technologically advanced civilization encounters a less advanced one, it usually goes badly for the less advanced civilization. European colonization of the Americas wiped out 90% of the indigenous population through disease, warfare, and displacement. British colonization of India, Africa, and Australia involved exploitation, extraction of resources, and violent suppression of resistance. Japanese expansion into Asia in the 1930s and 40s led to massacres and forced labor. Almost every example we have of contact between civilizations at different technological levels ends in conquest, exploitation, or genocide. Would alien civilizations be different? Maybe. Maybe a civilization advanced enough for interstellar travel would also be wise enough to have moved beyond conquest and exploitation. Maybe they would see value in diversity, in preserving other civilizations, in learning from different forms of life and intelligence. Or maybe not. Maybe the traits that allow a civilization to survive and expand, competitiveness, resource acquisition, elimination of threats, are the same traits that make them dangerous to encounter. Maybe becoming a spacefaring civilization requires a certain ruthlessness, and that ruthlessness doesn't go away just because you've developed advanced technology. We don't know, and that's the problem. The dark forest hypothesis says that in the face of this uncertainty, the only safe choice is silence and hiding. Don't reveal yourself. Don't attract attention. Survive by not being noticed. It's a bleak vision of the universe, but it fits the facts we observe. Complete silence from the cosmos, despite billions of years and billions of planets for civilizations to arise. The fourth possibility is stranger still. Maybe civilizations don't last long, for reasons that have nothing to do with self-destruction. Maybe they transcend. They move on to something else, something we can't detect or understand. Think about how quickly technology changes. 100 years ago, humans couldn't fly. The Wright brothers made the first powered flight in 1903. 50 years ago, computers filled entire rooms and had less processing power than a modern smartphone. The first computer with a gigabyte of storage was built in 1980 and cost $40,000. Now, you can buy a terabyte of storage, 1,000 gigabytes, for $50. 20 years ago, the internet was new, and most people didn't have email. The World Wide Web was invented in 1989, became publicly accessible in the early 1990s. 10 years ago, AI couldn't beat humans at Go, couldn't generate coherent text, couldn't create realistic images. Now, it can do all of those things. The pace of change is accelerating. Where will we be in another 100 years? Another 1,000 years? Another 1,000,000 years? Maybe advanced civilizations don't build Dyson spheres and starships. Maybe they move inward instead of outward. Maybe they discover that consciousness can be uploaded into computers, that biological bodies are unnecessary. Why live in a fragile biological body that ages and gets sick and dies when you can exist as pure information, immune to disease and aging and physical harm? Why colonize other planets, spending millions of years traveling between stars, when you can create entire universes inside computers? Simulated realities, indistinguishable from the physical one, but completely under your control. Maybe that's what happens to every civilization once they reach a certain level of technological sophistication. They realize that the physical universe is limiting, dangerous, and inefficient. Space is mostly empty. Resources are scattered across vast distances. Travel takes enormous amounts of energy and time. But inside computers, you can create any reality you want. You can run simulations where physics works differently, where you have different bodies, where you can explore possibilities impossible in the physical world. You can experience subjective millennia in what we would measure as seconds, living entire lifetimes, creating art and science and relationships, all inside the machine. So they create virtual realities and upload themselves into them. From the outside, it would look like the civilization just disappeared. One day they're broadcasting radio signals and building cities and launching spacecraft. Then they invent advanced computing and virtual reality. And over a period of maybe a few decades or centuries, they all upload themselves into machines. The radio signals stop, the cities fall silent, the spacecraft are abandoned. The planet becomes a dead world, dotted with server farms, running simulated universes for the minds that once lived there. Would we detect this? Probably not. A civilization living inside computers wouldn't need much external infrastructure. They wouldn't send out radio signals unless they wanted to be found. They wouldn't build Dyson spheres because they wouldn't need vast amounts of energy, just enough to run their servers. They might even power down most of their systems to reduce heat signature and avoid detection, running on minimal power, existing in a state of near hibernation to the outside observer. From our perspective, they would be effectively invisible. The galaxy could be full of civilizations like this, billions of uploaded minds living in simulated paradises, experiencing realities beyond our comprehension, completely invisible to our searches because they're no longer engaging with physical reality in any way we would recognize. This is called the transcension hypothesis. The idea that civilizations don't expand outward into space, they expand inward into complexity. They create denser and denser computational substrates, running faster and faster simulations, experiencing subjective millennia in objective seconds. Why would they care about the slow, cold, physical universe when they can create any reality they want inside their machines? Why would they communicate with primitive civilizations like us when they can simulate billions of entities to interact with, each one as complex and interesting as any biological being? We would be like ants to them, interesting from an academic perspective perhaps, but not worth engaging with directly. If this is what happens to most civilizations, then the Fermi Paradox is solved. They're out there, but they're not looking for us. They're not expanding. They're not visible. They've moved on to a mode of existence we can barely imagine and certainly can't detect. The fifth possibility is related, but even stranger. Maybe civilizations are out there, but we can't perceive them because they operate on a level of reality we haven't discovered yet. Maybe there's a whole layer of physics we're oblivious to, and advanced civilizations use that layer for communication, travel, and everything else. It's like the classic thought experiment about ants trying to understand the internet. The infrastructure is all around them, fiber optic cables buried in the ground, radio waves passing through their anthill constantly, electromagnetic signals carrying information at the speed of light. But ants have no way to perceive it or interact with it. They don't have the sensory organs to detect radio waves. They don't have the conceptual framework to understand digital information. From their perspective, nothing is there. The internet doesn't exist in their reality. Maybe we're the ants. Maybe the universe is full of activity, communication, travel, commerce, art, culture, all of it happening on a level or in a medium we haven't discovered yet. We're looking for radio signals because that's what we know, that's the technology we use. But maybe radio is ancient technology, abandoned billions of years ago in favor of something better. What might that something be? Quantum entanglement communication, using the strange property where measuring one particle instantly affects its entangled partner. regardless of distance. This is a real phenomenon in quantum mechanics. Einstein called it spooky action at a distance. Right now, we don't think you can use it to send information faster than light because you can't control what state the particle will be in when you measure it. But maybe advanced physics finds a way around that limitation. Neutrino messaging, using the nearly massless particles that pass through matter as if it weren't there. Trillions of neutrinos from the sun pass through your body every second, most of them never interacting with a single atom. They're almost impossible to detect. We need enormous detectors deep underground or under ice to catch even a handful of them. But maybe that's the point. If you want to send a message that can pass through planets and stars, that can't be intercepted or blocked, neutrinos might be perfect. Gravitational wave modulation, using ripples in space-time itself as a communication medium. We've only just begun detecting gravitational waves. Massive events like colliding black holes create ripples that we can barely detect with our most sensitive instruments. But maybe advanced civilizations can create and modulate gravitational waves for communication, or something we haven't even thought of yet. Some aspect of physics we don't know exists. Some dimension or field or property of reality that we're completely blind to because we haven't developed the theoretical framework or the instruments to detect it. If that's the case, then our SETI searches are looking in the right direction, but for the wrong thing. We're using a metal detector to search for radio signals when we should be using something we haven't invented yet to detect something we don't know exists. We could be surrounded by chatter, by communication, by evidence of intelligence, and we'd never know it. We'd keep looking up at the silent stars, wondering where everyone is, not realizing they're all around us, talking on frequencies we can't access. The sixth possibility is the zoo hypothesis. Earth is deliberately being preserved and protected, like a nature reserve or a zoo, and we're being observed, but not contacted. Assume the galaxy has one or more very advanced civilizations, millions or billions of years old. They've explored the galaxy, they've developed the ability to detect life on other planets. They know about us. They've probably been watching us for a long time, maybe since life first appeared on Earth, maybe since humans developed technology. Maybe they're watching right now. Why haven't they contacted us? Maybe they have rules, a kind of cosmic prime directive like in Star Trek. Don't interfere with developing civilizations. Let them evolve naturally. Don't contaminate their culture with outside influences. Don't give them technology they're not ready for. Wait until they reach a certain level of development and then make contact. The logic isn't unreasonable. Contact with a vastly more advanced civilization could be devastating to a younger one. Imagine if aliens landed tomorrow and gave us technology 1,000 years beyond our current level. Free energy, faster than light travel, medical technology that eliminates disease and aging, artificial intelligence far beyond anything we've developed, all of it handed to us fully formed. What would happen to human society? On one hand, it might solve a lot of problems. Climate change would become manageable with clean energy. Medical technology would save millions of lives. Transportation and communication would be revolutionized. We could expand into space, establish colonies on other worlds, ensure the survival of our species. On the other hand, it might cause total social collapse. What happens to the economy when all current technology becomes obsolete overnight? Millions of people work in energy, transportation, manufacturing, technology sectors. All of those jobs would disappear. What happens to people's sense of purpose and achievement when everything they've worked toward, every skill they've developed, every profession they've mastered, is suddenly made irrelevant by alien gifts? What happens to national power structures when technology is no longer something you develop, but something you receive? The countries that currently have advanced technology would lose their advantage. New power dynamics would emerge, possibly leading to conflict. What happens to religion and philosophy when confronted with beings so advanced they might as well be gods? Every religion would have to grapple with the existence of other intelligent beings. Are they part of God's plan? Do they have souls? Did they have their own prophets and revelations? For some people, this might strengthen their faith, proof that creation is vast and diverse. For others, it might shatter everything they believe. The cultural and psychological shock might be too much for our civilization to handle. Maybe advanced civilizations know this. Maybe they've tried making contact with developing civilizations in the past and watched those civilizations collapse under the weight of the revelation, unable to integrate the knowledge that they're not alone, that they're not special, that they're children being visited by adults. So now they wait. They observe from afar. They monitor our development, but they don't reveal themselves. Not until we're ready. And how do they know when we're ready? Maybe they have criteria, specific milestones they wait for. Technological milestones, interstellar travel, the ability to detect their presence, mastery of our own solar system, development of artificial intelligence, achievement of fusion power. Once we're advanced enough to find them on our own, that's when they make formal contact. Or maybe they wait for social milestones, a united planetary government, the elimination of war, the achievement of sustainability, some sign that we've matured as a species, that we can handle the responsibility of joining a galactic community. Maybe they're waiting for us to solve our problems on our own, to prove we can work together, to demonstrate wisdom and restraint before they trust us with knowledge and technology far beyond our current level. Until then, we're in quarantine, observed but not contacted, protected but isolated, like a nature preserve where researchers watch from hides and blinds, taking notes, documenting our development, but never interfering, never revealing themselves. If this is true, then Earth might be surrounded by observers right now, probes in orbit, sophisticated enough to be undetectable by our current technology, watching our every move. Ships in the outer solar system, in the Kuiper Belt or the Oort cloud, far beyond where we've sent our own spacecraft, recording our radio and television transmissions, analyzing our internet traffic, monitoring our progress. Bases on the far side of the moon, hidden in craters we haven't explored yet, or on asteroids we've never visited, or cloaked in ways we can't detect. All of them maintaining careful silence, watching us struggle with our problems, waiting to see if we pass whatever test they've set for us. The zoo hypothesis is impossible to prove or disprove. By definition, if they're hiding from us, we can't detect them. Any evidence we might find could be explained away as natural phenomena or human error. It's frustrating because it takes the question out of our hands. We can't make contact because they won't let us. We can search all we want, but we won't find anything because they don't want to be found. We're at their mercy, waiting for them to decide when and if we're ready. Some people find this comforting. The idea that we're being watched over, protected, that there's a plan and we're part of it. Others find it condescending. Who are they to decide when we're ready? What gives them the right to keep us in the dark? If they exist, we have a right to know. But maybe rights don't work that way when there's a billion-year gap in development. Maybe from their perspective, we're children, and you don't give children dangerous knowledge until they're mature enough to handle it. Whether that's patronizing or prudent probably depends on whether you're the child or the parent. So, those are the main solutions to the Fermi Paradox. We're alone because life is rare. Civilizations destroy themselves before they become visible. Everyone is hiding because contact is dangerous. They've transcended physical reality. They're here, but we can't perceive them. They're deliberately avoiding us until we're ready. And here's what makes this truly maddening. We can't rule any of them out yet. Each one remains possible, given what we currently know. Let's talk about what we're actually doing to answer this question, because the search isn't just theoretical speculation, it's active, ongoing science with real telescopes, real data, and real scientists dedicating their careers to it. SETI, the search for extraterrestrial intelligence, has been operating in various forms since 1960. Frank Drake conducted the first modern SETI experiment, called Project Ozma, using a radio telescope in West Virginia. He pointed it at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for narrowband radio signals that might indicate artificial origin. He found nothing. But it was just the beginning. Since then, SETI has expanded enormously. The SETI Institute, founded in 1984, coordinates much of this research. They use radio telescopes around the world to scan millions of frequency channels, looking for signals that stand out from the background noise of the universe. Natural radio sources exist everywhere. Pulsars emit regular pulses of radio waves, the rotating neutron stars sending out beams like cosmic lighthouses. Quasars and other active galactic nuclei emit radio waves from supermassive black holes consuming matter. Even Jupiter emits strong radio signals from charged particles trapped in its magnetic field. But these all have characteristic patterns. They're broadband, spread across many frequencies, or they're irregular but changing in predictable ways based on rotation or orbital mechanics. An artificial signal would be different. It would likely be narrowband, concentrated at a specific frequency to maximize signal strength and minimize the power needed to transmit it. Think about how we design radio transmitters on Earth. We don't spray energy across the entire spectrum. We focus it at specific frequencies because that's more efficient. An alien civilization would probably do the same. The signal might be modulated, carrying information in the form of pulses or frequency changes or amplitude variations. It might repeat on a regular schedule, allowing receivers to confirm it and distinguish it from random noise. It might contain mathematical patterns, prime numbers or pi, or something that clearly couldn't be produced by natural processes. SETI researchers have developed sophisticated algorithms to search for these patterns in the noise. They process billions of data points every day, looking for anything unusual. Most of what they find is interference, satellites in Earth orbit, aircraft radar systems, cell phone towers, microwave ovens, all of it creating signals that can be mistaken for extraterrestrial sources until you trace them back to their terrestrial origin. Every few years, there's a signal that can't be immediately explained. Researchers get excited. They follow up. They point telescopes at the same location. They try to detect it again. And usually, after days or weeks of investigation, it turns out to be something mundane. A satellite in an unusual orbit that wasn't in the catalogue. A military radar system operating on an unexpected frequency. Equipment malfunction, creating a false signal. The WOW signal remains the most famous, unexplained detection. On August 15, 1977, The Big Ear radio telescope at Ohio State University detected a strong, narrow-band signal at 1.420 MHz, very close to the hydrogen line, a frequency that astronomers have long thought would be a logical choice for interstellar communication, because hydrogen is the most abundant element in the universe. The signal lasted 72 seconds, exactly as long as you'd expect for a signal from a fixed point in the sky as the Earth's rotation carried the telescope's beam across it. The astronomer who saw the printout was so startled he wrote, "Wow," in the margin, hence the name. It matched all the criteria for an artificial signal: narrowband, strong, at a meaningful frequency, appearing once and then gone, but it never repeated. Researchers have pointed telescopes at that same spot in the sky hundreds of times since 1977, using more sensitive equipment, scanning broader frequency ranges, listening for longer periods. Nothing. Complete silence. Was it aliens? Probably not. In 2017, a team of researchers suggested it might have been caused by a passing comet releasing hydrogen, though others dispute this explanation. The point is, in over 40 years of searching, that's the best candidate we've found. One ambiguous signal that never repeated, and probably wasn't artificial anyway. That's it. Everything else is silence. SETI has also expanded beyond radio. Optical SETI looks for laser pulses from other star systems. A sufficiently powerful laser could outshine a star for a brief moment, creating a detectable flash. If a civilization wanted to signal its presence efficiently, a pulsed laser might be a better choice than radio. More directional, more energy efficient, less likely to be drowned out by natural sources. Think about it. Radio waves spread out in all directions, diluting as they travel. A laser beam stays focused, all the energy going in one direction. If you wanted to send a message to a specific star system and you had limited power, you'd use a laser. So far, optical SETI has found nothing conclusive. But the search is still in its early stages. We've only been looking seriously for optical signals for a couple of decades, and we're limited to observing the brightest, most obvious pulses. There could be fainter signals we're missing. Then there's the search for techno-signatures, signs of technology that might be visible even if a civilization isn't deliberately trying to communicate. Dyson spheres or swarms would have a distinctive infrared signature. The star's visible light blocked or dimmed, but heat radiated in the infrared from the structure, collecting all that energy. We've conducted surveys looking for stars with this signature, stars that are dim in visible light, but bright in infrared in a way that can't be explained by dust or other natural phenomena. We've found candidates, unusual stars that don't fit normal categories, but when we investigate further, we always find natural explanations. Atmospheric pollution from industrial processes might be detectable in exoplanet atmospheres. On Earth, our atmosphere contains chemicals that wouldn't be there without industrial civilization. Chlorofluorocarbons from refrigerants, nitrogen dioxide from combustion, compounds created by manufacturing processes. If we can detect these in the atmosphere of a planet orbiting another star, that would be strong evidence of technology. The James Webb Space Telescope, launched in 2021, has the sensitivity to potentially detect these signatures if they're present in sufficient concentrations on nearby exoplanets. City lights on the night side of a planet could potentially be seen with advanced enough telescopes. We've taken photographs of Earth from space, showing the glow of our cities at night, a clear sign of technological civilization. If we can see this on exoplanets, it would be unambiguous evidence. We're not quite there yet, technologically, but we're getting closer. Spacecraft engines using nuclear propulsion might create detectable radiation signatures. If a civilization is launching interstellar missions, the exhaust from their engines might be visible as unusual radiation patterns. This is speculative, but it's something we could potentially detect. All of this falls under the umbrella of technosignatures, and it's an expanding field of research that's finally being taken seriously by mainstream astronomy. NASA has started funding technosignature research. In 2018, they held a workshop bringing together astronomers, engineers, and theorists to discuss how we might detect evidence of technology in space. This was significant because for decades, SETI was considered fringe science, not quite respectable. Legitimate astronomers studied stars and galaxies and black holes. Looking for aliens was something you did on your own time, not with major institutional support or public funding. That's changing. The discovery of thousands of exoplanets has made it respectable to ask whether any of them harbor life. And if we're asking whether they have life, it's not much of a stretch to ask whether they have intelligent life. If we're going to spend billions of dollars building telescopes to study exoplanet atmospheres looking for oxygen and methane, why not also look for signs of technology? The pendulum is swinging from dismissal to serious investigation. Part of this shift is due to advances in technology. We can now study exoplanet atmospheres in detail, something that was science fiction just a few decades ago. The first exoplanet, orbiting a sun-like star, was discovered in 1995. Now we've found thousands, and we're analyzing their atmospheres, measuring their sizes and masses, determining which ones might be habitable. The James Webb Space Telescope has already transformed our ability to study distant objects. Its infrared instruments can see through dust that blocks visible light. It can analyze the chemical composition of exoplanet atmospheres by watching how starlight filters through them during transits. If there's oxygen being produced by photosynthesis, if there's methane from biological processes, if there's anything unusual that can't be explained by geology and chemistry alone, JWST has a real chance of finding it. We're also getting better at detecting small, rocky planets in habitable zones. These are the worlds most likely to have conditions suitable for life as we know it. The Kepler mission, which operated from 2009 to 2018, found thousands of exoplanets by watching for the tiny dips in starlight that occur when a planet passes in front of its star. Follow-up missions, like TESS, the Transiting Exoplanet Survey Satellite, launched in 2018, are finding thousands more, surveying nearby bright stars that are easier to study in detail. Each discovery expands our understanding of how common different types of planets are, and the answer so far is that planets are incredibly common. Rocky planets are common. Planets in habitable zones are common. Many of them are in conditions where life could potentially exist. This makes the silence even more puzzling. We keep finding places where life could arise, tens of billions of potentially habitable worlds just in our galaxy, but we're not finding any evidence that it has. Let me talk about the Drake equation in more depth, because it's a useful framework for understanding our uncertainty. Frank Drake developed this equation in 1961 as a way to estimate the number of detectable civilizations in our galaxy. It looks like this. N equals R star times Fp times Ne times Fl times Fi times Fc times L. N is the number of civilizations in the Milky Way with detectable signals. R star is the rate of star formation in the galaxy. Fp is the fraction of stars with planets. Ne is the number of planets per star system in the habitable zone. FL is the fraction of habitable planets that actually develop life. Fi is the fraction of life-bearing planets that develop intelligence. FC is the fraction of intelligent civilizations that develop detectable technology. L is the length of time such civilizations release detectable signals. We know some of these numbers pretty well now. R star. The rate of star formation is roughly 1 to 3 new stars per year in the Milky Way. The galaxy has been doing this for billions of years, which is why there are hundreds of billions of stars. P. The fraction of stars with planets is close to 1. Exoplanet surveys have confirmed that almost every star has planets. This was a surprise when the first exoplanets were discovered, but it's now well established. Planets form naturally from the disks of gas and dust that surround young stars. NE, the number of habitable zone planets per star. Current data suggests somewhere around 0.1 to 0.5. For every 10 stars, there's probably 1 to 5 potentially habitable planets. That's tens of billions of potentially habitable planets in the Milky Way. But the other variables, FL, Fi, FC, and L, we just don't know. FL, the fraction of habitable planets that develop life, could be close to 1 if life arises easily whenever conditions are right. Or it could be 1 in a trillion if the origin of life requires an incredibly unlikely sequence of chemical events. Does that mean life is easy, or that we got lucky? We're working on answering this question by searching for life elsewhere in our solar system. Mars might have had life in the past when it had liquid water on its surface billions of years ago. We've sent rovers to search for evidence: organic molecules, fossil microbes, chemical signatures that would indicate biological processes. The Curiosity rover, which landed in 2012, has found complex organic compounds in rocks that are 3 billion years old. The Perseverance rover, which landed in 2021, is collecting samples from an ancient river delta, rocks that formed in an environment that could have supported microbial life. These samples will eventually be returned to Earth for detailed analysis. So far, we haven't found definitive proof of life, but we've found that Mars had the ingredients: water, organic molecules, energy sources. Whether those ingredients combined to create life is still unknown. Europa, one of Jupiter's moons, has a global ocean under its icy crust, possibly containing more water than all of Earth's oceans combined. That ocean has been stable for billions of years, kept liquid by tidal heating from Jupiter's gravity squeezing and flexing the moon. The ocean might have contact with the rocky seafloor below, creating hydrothermal vents similar to those on Earth where hot, mineral-rich water spews into the cold ocean. On Earth, these vents support entire ecosystems of organisms that don't rely on sunlight for energy. They use chemosynthesis instead of photosynthesis, extracting energy from chemical reactions between the hot vent fluids and the cold seawater. If Europa has similar vents, it might have similar life. NASA is planning the Europa Clipper mission to study this moon in detail, launching in 2024 and arriving at Jupiter in the early 2030s. It won't land on Europa, but it will make multiple close flybys, using radar to probe through the ice and determine the thickness of the shell, using mass spectrometry to analyze the composition of material ejected from the surface. If there are organic molecules, if there are signs of biological activity, Clipper might detect them. Enceladus, a small moon of Saturn, also has a subsurface ocean that vents water into space through geysers at its south pole. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, flew through these plumes multiple times. It detected water vapor, ice particles, salt, silica, and complex organic molecules, including some that on Earth are associated with biological processes. The silica particles suggest hydrothermal activity, hot water interacting with rock at the ocean floor. The organic molecules include some with molecular weights over 200, complex enough to be interesting from a biological perspective. Enceladus is much smaller than Europa, only about 310 miles in diameter, about the size of Arizona. But its ocean is accessible. The plumes spray material directly into space where spacecraft can sample it. A future mission could fly through the plumes with more sophisticated instruments, specifically designed to detect biosignatures and potentially discover life without ever having to land. Titan, Saturn's largest moon, is another intriguing target. It has a thick atmosphere, liquid methane and ethane lakes on its surface, and possibly a subsurface water ocean as well. The surface is far too cold for liquid water, temperatures around -180 degrees Celsius. But the liquid hydrocarbons could potentially support a completely different kind of chemistry, maybe even a different kind of life based on methane instead of water. This is speculative, but Titan's complex organic chemistry makes it worth investigating. NASA and ESA are planning the Dragonfly mission, a nuclear-powered quadcopter that will fly through Titan's atmosphere and land at multiple sites to study the chemistry. It's scheduled to launch in 2027 and arrive at Titan in the mid-2030s. If we find life on Mars or Europa or Enceladus or Titan, even simple microbial life, it would be transformative for our understanding of FL in the Drake equation. It would tell us that life isn't unique to Earth, that it can arise independently on other worlds. And if it happened multiple times in one solar system, it's probably common throughout the universe. That would change our estimate of FL from completely unknown to probably close to 1, at least for simple microbial life. Finding complex life would be even more significant. It would tell us that the jump from simple to complex isn't impossibly rare. But even finding only simple life on multiple worlds would be huge, because it would suggest that the hard filter isn't the origin of life, it's somewhere else, either in the evolution of intelligence or in the survival of technological civilizations. But even if life is common, that doesn't mean intelligence is common. FI, the fraction of life-bearing planets that develop intelligence, is completely unknown. On Earth, intelligence evolved relatively recently. Life existed for over 3 billion years before anything remotely intelligent appeared. Most animals aren't capable of abstract thought or tool use or asking questions about the universe. Humans are unusual. Our intelligence is quantitatively and qualitatively different from other species. Why did intelligence evolve in our lineage? What were the specific pressures that favored bigger brains, better problem-solving, more sophisticated communication? We have theories, but we don't fully understand it. And if we don't understand why it happened here, we can't predict whether it would happen elsewhere. Maybe intelligence is a common outcome of evolution, something that arises whenever there's competition and complexity. Or maybe it's a rare fluke, a combination of factors so specific that it only happens once in a billion planets. We don't know. FC. The fraction of intelligent species that develop technology adds another layer of uncertainty. Humans developed technology, but would all intelligent species? Dolphins are smart, but they live in an environment where fire is impossible, and without fire, metallurgy is impossible, and without metallurgy, Advanced technology is much harder to develop. Octopuses are remarkably intelligent, but they're solitary and short-lived. They don't pass knowledge between generations the way humans do. What if intelligence evolves in a species without hands or other manipulative appendages? You need to be able to make and use tools to develop technology. What if intelligence evolves in a species that lives underground, or in caves, or on a planet with thick cloud cover that makes astronomy impossible? Without being able to see the stars, would they even think about space? Would they develop the motivation to leave their planet? So, Fi and Fc together represent huge uncertainties about whether intelligence arises and whether it leads to technology. And then there's L, the length of time civilizations remain detectable. If civilizations destroy themselves after a few centuries, L is small, maybe 100 to 500 years. If they survive, but stop broadcasting, either because they transcend or because they switch to more efficient communication methods that we can't detect, L is still small. If they last for millions of years and continue broadcasting the entire time, L is large. We have no idea which is more likely. When you plug reasonable estimates into the Drake equation, you get wildly different answers depending on what assumptions you make. Optimistic assumptions: life is common, intelligence is common, civilizations last a long time. You get thousands or millions of detectable civilizations in the galaxy. We should be able to detect dozens or hundreds of them with our current technology. Pessimistic assumptions: life is rare, intelligence is very rare, civilizations are short-lived. You get much less than one. Just us, alone. The equation doesn't give us an answer. It gives us a framework for understanding our ignorance, for identifying which questions we need to answer to solve the Fermi Paradox. But here's what we can say with some confidence. If the optimistic numbers are anywhere close to right, we should have detected something by now. We've been searching seriously for over 60 years. We've scanned millions of stars. We've analyzed thousands of exoplanets. We've looked for radio signals and optical pulses and technosignatures. The fact that we haven't found anything suggests either the pessimistic numbers are closer to reality or something else is going on that we haven't thought of. Some factor we don't understand that's filtering out civilizations or making them invisible to our searches. The future of the search looks promising from a technological standpoint. New telescopes, new instruments, new methods of analysis are coming online or being planned. The Square Kilometre Array, currently under construction in South Africa and Australia, will be the most sensitive radio telescope ever built when it's completed. Its total collecting area will be about 250 acres of radio dishes and antennas working together. It will be able to detect signals far weaker than anything we can currently see. It will be able to scan large portions of the sky simultaneously. It will operate across a wide range of frequencies. If there are civilizations out there broadcasting, even unintentionally, even just the everyday radio leakage from their technology, SKA will have the best chance yet of finding it. Ground-based optical telescopes are getting bigger too. The extremely large telescope in Chile, set to begin operations in the late 2020s, will have a mirror 39 meters in diameter. For comparison, the largest optical telescopes currently operating have mirrors around 10 meters in diameter. The ELT will gather far more light, allowing it to see fainter objects and study them in more detail. These telescopes will be able to take direct images of exoplanets, not just detecting them indirectly by their effect on their star, but actually photographing them. They'll be able to analyze exoplanet atmospheres with much greater precision than we can now, searching for biosignatures and technosignatures. Space-based telescopes are also advancing. The James Webb Space Telescope is just the beginning. Proposals for even larger space telescopes are being developed. Instruments specifically designed to study exoplanets, to take high-resolution images of them, to search for signs of life and intelligence. We're also improving our signal processing algorithms. Machine learning and artificial intelligence are being applied to SETI data, allowing us to search for patterns that might not fit our preconceptions of what an alien signal should look like. Traditional SETI looks for narrowband signals, regular pulses, mathematical patterns. But what if alien communication doesn't fit those categories? What if it looks like noise to us because we don't understand the encoding? Machine learning can potentially identify anomalies that human researchers would miss, patterns that are statistically significant but don't match any known natural or artificial source. Citizen science is also playing a role. Projects like SETI at Home, which ran from 1999 to 2020, allowed millions of volunteers to donate their computer's idle processing time to analyze radio telescope data. It didn't find any alien signals, but it processed an enormous amount of data and demonstrated that distributed computing can tackle problems too large for any single institution. New projects are emerging that will continue this approach, allowing people around the world to participate in the search. Breakthrough, Listen, funded by billionaire investor Yuri Milner and launched in 2015, is the most comprehensive SETI program ever undertaken. It's surveying 1 million nearby stars, the 100 closest galaxies, and the entire galactic plane. It's listening across a frequency range from 500 MHz to 50 GHz, covering billions of individual channels. It's using some of the world's most powerful telescopes, including the Green Bank Telescope in West Virginia and the Parkes Telescope in Australia. If there are signals out there that fit any reasonable definition of artificial, Breakthrough Listen has the best chance yet of finding them. Let me tell you about some specific cases that have generated excitement in the SETI community, because they illustrate both the promise and the challenges of the search. Tabby's star, officially designated KIC 84628552, became famous in 2015 when a group of citizen scientists analyzing data from the Kepler Space Telescope noticed something very strange. The star's brightness was dimming irregularly, sometimes by as much as 22% over periods of days. This was unprecedented. When a planet passes in front of a star, a transit, it blocks a tiny fraction of the star's light, usually 1% or less for a Jupiter-sized planet, much less for an Earth-sized planet. But Tabby's star was dimming by 22%. Something very large, or a lot of smaller somethings, were blocking the light. Initial speculation went wild. Could this be evidence of megastructure construction? A Dyson sphere or swarm being built around the star? Alien engineering, on a scale we could actually detect? Astronomer Tabetha Boyajian, after whom the star is nicknamed, was cautious but couldn't rule it out. No natural explanation fit all the observations. The dimming patterns were irregular, asymmetric, not what you'd expect from planets or asteroids or comets. The SETI community took notice. Researchers pointed radio telescopes at Tabby's star, listening for signals. They looked for infrared excess, the heat signature you'd expect from a structure collecting energy from a star. If something was blocking 22% of the star's light, that energy had to go somewhere. It should show up as infrared radiation. They didn't find it. No excess infrared, no radio signals, no other anomalies besides the strange dimming. Further observations showed that the star was also dimming overall, getting fainter over years, not just experiencing periodic dips. And the amount of dimming varied with wavelength. Blue light was blocked more than red light. This suggested dust, tiny particles that scatter blue light more effectively than red light, the same reason Earth's sky is blue. Eventually, the most likely explanation emerged. A cloud of comets or debris, possibly from a shattered planet or a recent collision, passing between us and the star. The irregular dimming would be caused by clumps of debris of different sizes and densities passing in front of the star at different times. The overall dimming would be caused by a larger diffuse cloud gradually moving across our line of sight. The wavelength dependence fits with dust particles. It's probably natural, not artificial. But for a while, it was genuinely mysterious, and it showed that we could detect large-scale structures around other stars if they existed. The fact that Tabby's star turned out to be natural is actually useful information. It tells us that weird dimming patterns don't automatically mean alien megastructures. We have to rule out natural explanations first, and nature is capable of producing phenomena we didn't expect. Another case that generated enormous excitement was Oumuamua, the first confirmed interstellar object to pass through our solar system. In October 2017, astronomers at the Pan-STARRS telescope in Hawaii detected an object moving through the inner solar system at high speed. Its trajectory was hyperbolic, meaning it wasn't bound to the sun's gravity. It came from interstellar space and would leave the solar system and never return. This was the first time we'd detected an object that definitely originated from outside our solar system. Oumuamua, Hawaiian for scout or messenger, was strange in several ways. Its shape was unusual, either very elongated like a cigar, about 400 meters long and 40 meters wide, or flat like a pancake. We couldn't tell for sure because we never got close enough for detailed imaging. It was tumbling end over end as it traveled, rotating every 7 to 8 hours. And as it left the solar system, it accelerated slightly, more than could be explained by the sun's gravity alone. This acceleration was unexpected. Comets accelerate as they leave the solar system because ice on their surface evaporates, creating jets of gas that act like tiny rocket engines. But Oumuamua didn't show any signs of outgassing. No tail, no coma of gas and dust around it. It looked like an asteroid, but it was accelerating like a comet. Harvard astronomer Avi Loeb suggested a radical explanation. What if Oumuamua was artificial? What if it was a light sail, a spacecraft using solar radiation pressure for propulsion? A thin reflective sheet would accelerate from sunlight without producing any visible gas or dust. The elongated or pancake shape would make sense for a sail. The tumbling motion might indicate that it was derelict, no longer under active control. Loeb wrote a paper about this possibility, and later, a book. He argued that we should consider the artificial hypothesis seriously, that dismissing it out of hand was unscientific. Most astronomers disagreed. They argued that Oumuamua was almost certainly natural, probably a comet made of unusual material that outgassed in ways we didn't detect, or a fragment from a larger object shattered by tidal forces. The problem was that Oumuamua left the solar system quickly, and we didn't have instruments in position to study it in detail. By the time we realized how unusual it was already too faint to observe with most telescopes. We got a few weeks of observations, not enough to definitively determine what it was. Was it artificial? Probably not. Almost certainly not. But we can't say with absolute certainty. And that uncertainty drives home an important point. If we detect something unusual, we need to study it immediately and thoroughly, because opportunities can slip away fast. The solar system is huge, and objects moving through it at interstellar speeds don't stick around for long. If Oumuamua was artificial, if it was a probe or a derelict spacecraft from another civilization, then we missed our chance to confirm it. If it was natural, which is far more likely, then it taught us that interstellar objects can have properties we didn't expect, and we need better tools to study them. NASA and other space agencies are now developing plans for missions that could intercept the next interstellar visitor. If we detect another object like Oumuamua early enough, while it's still in the outer solar system approaching the Sun, we could potentially launch a spacecraft to rendezvous with it. Take close-up images, analyze its composition, determine once and for all whether it's natural or artificial. There have been other intriguing signals over the years. In April 2019, astronomers detected a signal they called BLC-1, Breakthrough Listen Candidate 1. It was a narrowband signal at 982 MHz, detected during observations of Proxima Centauri, the closest star to our Sun. Proxima Centauri is only 4.2 light-years away, and it has at least 2 planets. One of them, Proxima Centauri b, is in the habitable zone. The signal appeared to shift in frequency over time, in a way consistent with the Doppler effect, from a source on a rotating planet. It didn't repeat in subsequent observations. Researchers spent months analyzing the signal, trying to determine if it was artificial or just interference. Eventually, they concluded it was probably interference from human technology, a radio transmitter or electronic equipment, creating a signal that happened to appear during the observation of Proxima Centauri. But the analysis process showed how thorough SETI researchers are. They didn't jump to conclusions. They didn't announce the detection publicly until they'd ruled out every possible source of interference they could think of. And even then, they presented it as a candidate, not a confirmed detection. The challenge is that Earth is awash in radio signals. We have millions of transmitters, satellites, cell phones, Wi-Fi routers, radar systems, all of them creating signals that can leak into telescope observations. Distinguishing an extraterrestrial signal from terrestrial interference is incredibly difficult. You need to see the signal multiple times, confirm that it comes from the same location in the sky, verify that it moves with the stars rather than with Earth-based transmitters, rule out satellites and aircraft, and every other possible source of contamination. This takes time and careful analysis, and even then, you can't be completely certain unless the signal contains information that's unambiguously artificial, like a message or a pattern that couldn't occur naturally. Another challenge is that we don't know what alien signals might look like. SETI searches for narrowband signals because that's how we transmit information efficiently, focusing energy at specific frequencies. But maybe aliens use different methods, spread spectrum techniques that look like noise unless you know the encoding, or ultra-wideband pulses, or modulation schemes we haven't invented yet. We're looking for signals that resemble our own technology, but there's no guarantee that aliens would use similar approaches. This is the streetlight effect, searching where the light is good rather than where you lost your keys. We search for narrowband radio signals, not necessarily because that's where aliens are most likely to be, but because that's what we know how to search for. But even with all this technology, all this effort, we might not find anything. And that's okay, because the search itself is valuable. Every star we examine and find nothing teaches us something about the distribution of civilizations, or lack thereof. Every exoplanet we study expands our understanding of planetary science, how planets form, how atmospheres evolve, what makes a world habitable. Every null result refines our estimates in the Drake equation, helping us narrow down the values of those unknown variables. Science isn't just about finding positive results. It's about narrowing down the possibilities, eliminating wrong answers, getting closer to truth, even when that truth is disappointing. And honestly, finding nothing would be an answer. Not the answer we might hope for, but an answer nonetheless. If we search for another century, another 1,000 years, with ever-improving technology, scanning ever more stars and planets, and we find nothing, at some point, we have to conclude that intelligent life is extraordinarily rare, maybe unique to Earth, and that would transform how we think about ourselves and our responsibility to the cosmos. If we're the only ones, if consciousness exists nowhere else in the observable universe, then everything depends on us. The future of intelligence, possibly the only intelligence, rests on whether we can survive and spread to other worlds. It's a heavy burden, but also a profound privilege. We would be the ancestors of all future intelligence, the seed from which a cosmic civilization grows, the first ones to ask these questions and the only ones to carry the answers forward. On the other hand, if we do find something, if we detect a signal or a biosignature or any evidence of life beyond Earth, that's equally transformative. It would be the most important discovery in human history, answering the oldest question we've ever asked: are we alone? The answer would be no, we are not alone, and the psychological and philosophical impact would be enormous. Religions would have to grapple with the existence of other intelligent beings. Are they part of creation? Do they have souls? Did they have their own prophets and revelations? For some people, this might strengthen their faith, seeing it as proof that creation is vast and diverse. For others, it might challenge fundamental beliefs about humanity's special place in the universe. Philosophy would have to expand its scope. Ethics, politics, art, culture, everything we've developed as uniquely human might turn out to be universal, or at least not unique. Questions about consciousness, morality, the nature of intelligence would have new data points to work with. Science would be revolutionized. We could learn from their biology, their technology, their understanding of physics. Even a simple signal confirming their existence would change everything, because it would tell us that intelligence can survive, that civilizations can last long enough to make themselves known, that the great filter, if it exists, can be passed. It would tell us there's hope, that we're not doomed to destroy ourselves, that someone out there figured out how to survive their technology and thrive, unless the signal is a warning. Unless it says, "Stay quiet, don't reveal yourselves, the galaxy is dangerous, we made a mistake by broadcasting, and now we're telling you not to make the same mistake." Then we'd have a different set of problems to worry about, knowing that contact is possible, but potentially fatal. That, revealing ourselves, might be the worst thing we could do. The point is, we're living in a unique moment in human history. We have the technology to seriously search for extraterrestrial intelligence for the first time. Previous generations could only wonder, looking up at the stars and imagining. Future generations might have an answer, definitive proof one way or the other. We're the ones in the middle, actively looking, on the cusp of potentially finding something or determining that there's nothing to find. That's exciting and terrifying in equal measure. We're the first generation capable of answering the question, and possibly the last generation that will ask it in ignorance. Within our lifetimes, or our children's lifetimes, we might know. And while we're searching, while we're building telescopes and scanning the skies and analyzing data, we're also sending out our own signals. We've been broadcasting radio and television for over a century. Those signals are expanding outward in a bubble, now over 200 light-years in diameter, traveling at the speed of light, carrying information about Earth and humanity to anyone who might be listening. Any civilization within that bubble, with sensitive enough equipment, could detect us. They would know we're here. They would know we're a technological civilization. They would know we're not deliberately hiding. What would they make of our signals? If they could decode our television broadcasts, if they could understand the images and sounds we send out, they would get a strange and confusing picture of humanity. News reports of wars and disasters, genocides and famines and natural catastrophes, sitcoms and dramas, fictional stories about fictional people in fictional worlds. Reality TV showing people competing for money or fame. Sports, humans running and jumping and throwing balls, celebrating victories and mourning defeats. Advertisements for products they can't buy, appeals to desires they might not understand. Would they understand any of it? Would they recognize it as communication, as art, as culture? Would they think we're worth contacting? Or would they look at our broadcasts and decide we're too primitive, too chaotic, too violent, too strange to bother with? We don't know. We can't know until they respond, if they ever do. We've also sent deliberate messages. The Arecibo message in 1974 was a brief radio transmission aimed at the globular cluster Messier 13, containing information about Earth, about humans, about where we are in the galaxy. It won't get there for about 25,000 years, and any reply won't reach us for another 25,000 years after that. It was more symbolic than practical, a demonstration that we could send signals to the stars, but not a realistic attempt at two-way communication. The golden records on Voyager 1 and Voyager 2 are more enduring. These spacecraft, launched in 1977, contain sounds and images from Earth, music from different cultures, greetings in multiple languages, pictures of humans and animals and landscapes, diagrams showing where Earth is and what we look like. The records are designed to last billions of years, far longer than our civilization might survive. Voyager 1 is now in interstellar space, beyond the influence of the Sun, traveling at about 10.6 miles per second. In about 40,000 years, it will pass within about 1.6 light-years of a star called Gliese 445. If anyone is there, if they intercept the spacecraft, if they can figure out how to play the record, they'll hear us. They'll hear Chuck Berry and Beethoven. They'll hear waves crashing on a beach and wind blowing through trees. They'll hear a baby crying and people laughing. They'll see what we look like, what our world looks like, what we consider beautiful and important. And they'll know that we existed, that we sent this message, that we hoped someone would find it. That's simultaneously beautiful and melancholy. Beautiful because it's an act of hope and connection, reaching out across the void, sending a message to beings we'll never meet, across distances we'll never cross. With hope, we might not live to see fulfilled. Melancholy, because by the time anyone finds it, if anyone ever does, we might be long gone. Our civilization might have collapsed, our species might be extinct, Earth might be a dead world, but the golden record will still be out there, drifting through the galaxy, carrying a snapshot of who we were in 1977. A time capsule of a species that once looked up at the stars and wondered if anyone was looking back. That's the human story in a nutshell. We're brief, fragile, temporary, but we create meaning anyway. We build, we explore, we ask questions, we send messages to beings we'll never meet, we reach for knowledge we might not live to see, and maybe that's enough. Maybe the search for extraterrestrial intelligence isn't really about finding aliens. Maybe it's about understanding ourselves, about defining what it means to be intelligent, to be aware, to be part of something larger than ourselves. The Fermi Paradox forces us to confront these questions. Are we special or ordinary, alone or part of a cosmic community, destined for greatness or headed for extinction? The answer matters because it shapes how we see our place in the universe and our responsibility to the future. If we're alone, then life is incredibly precious and fragile. We're the only place in the universe where matter has organized itself to contemplate existence, to create art and music and science, to ask why. We can't afford to screw it up, because if we destroy ourselves, all of that is lost, not just for Earth, but for the entire universe. The concept of love, the sound of music, the appreciation of beauty, the capacity for wonder, all unique to this one planet, and if we blow it, the universe loses something it will never get back. That's a staggering responsibility. Every decision we make about nuclear weapons, about climate change, about artificial intelligence, about how we treat our planet and each other, carries cosmic weight. We're not just deciding our own fate, we're deciding whether consciousness continues to exist in the universe or disappears forever. Think about what that means practically. It means we can't afford another world war. We can't afford a runaway pandemic. We can't afford to wreck our planet's climate beyond recovery. It means we need to become a multi-planetary species, spreading to Mars and beyond, ensuring that if something catastrophic happens to Earth, intelligence survives somewhere else. It means we need to develop the political and social institutions capable of managing existential risks, which we currently don't have. We need a way to coordinate global responses to global threats, to make decisions on timescales longer than election cycles, to prioritize long-term survival over short-term gain. This is extraordinarily difficult. Humans evolved to care about their immediate tribe, their family, their community. We're good at dealing with threats we can see and touch, predators and rivals and natural disasters. We're not good at dealing with abstract, long-term, global threats like climate change or AI risk or asteroid impacts. Our brains didn't evolve to think on those timescales or those spatial scales. But if we're alone, we have to overcome those limitations. We have to expand our circle of concern, from our tribe to our species to all future generations. We have to think in centuries and millennia, not just years and decades. We have to cooperate on a global scale, setting aside national interests for the survival of consciousness itself. This is probably the hardest thing any species has ever attempted. It's not just technological, it's psychological and political and cultural. It requires changing how we think, how we organize ourselves, what we value. Many people, probably most people, don't think this way. They care about their own lives, their families, their countries. Abstract concerns about the survival of intelligence in the universe don't motivate action the way immediate personal concerns do. But if we're alone, those abstract concerns are the most important thing there is. Everything else, all the political squabbles and economic competition and cultural conflicts, fades to insignificance compared to the question of whether we survive. On the other hand, if we're not alone, if there are other civilizations out there, that changes the equation. We're not carrying the entire burden of consciousness in the universe. If we fail, if we destroy ourselves, Intelligence continues elsewhere. That's both comforting and humbling. Comforting because the stakes are lower, we're not risking everything. Humbling because we're not as special as we might have thought, we're just one of many, perhaps one of millions. But even if we're not alone, we still have a responsibility to survive and thrive. Because every civilization that exists, every place where consciousness has emerged, is valuable and unique. We might share the universe with others, but we're still the only us, the only species with human art and music and literature, the only ones who have experienced Earth's specific history and environment. If we disappear, that's lost, even if other civilizations continue. And there's another consideration. If we make it through the Great Filter, if we survive our technological adolescence and become a mature, spacefaring civilization, we might eventually meet those other civilizations. First contact could be the most important event in human history. It would tell us we're not alone, that we're part of a larger community, that there are others out there to learn from and possibly to cooperate with. But first, contact could also be dangerous. The dark forest hypothesis might be correct. Revealing ourselves might be a fatal mistake. Or the other civilization might be so different from us, so alien in their psychology and values, that meaningful communication is impossible. Or they might be friendly, but so advanced that interacting with them changes us in ways we can't predict or control. This is why some scientists argue we should be very cautious about broadcasting our presence. METI, messaging to extraterrestrial intelligence, is controversial. Should we announce ourselves to the cosmos, or should we listen quietly and wait to hear from others first? Those who support METI argue that we've already revealed ourselves through our radio and television broadcasts, our radar signals, all the electromagnetic noise of industrial civilization. It's too late to hide. Anyone within 100 light years could already detect us. We might as well send deliberate messages, carefully crafted to convey information about who we are and what we value. Maybe those messages will be the first thing aliens notice, more obvious than our incidental leakage. Those who oppose METI argue that deliberate broadcasts are far more detectable than incidental leakage. Our TV and radio signals are weak. They degrade quickly with distance. They're not specifically aimed at any particular star system. A deliberate message, a powerful, focused transmission aimed at nearby stars, would be much more obvious. It would be like the difference between the ambient light from a city and a searchlight pointed at the sky. Both are visible, but one is far more noticeable. Moreover, they argue, we don't know what's out there. We don't know if the galaxy is full of friendly civilizations waiting to welcome us, or hostile ones waiting for prey, or something in between. Until we know more, until we've surveyed more of the galaxy and found evidence one way or the other, we should maintain some degree of caution. We should listen before we speak, observe before we reveal ourselves. This debate isn't resolved, and it probably won't be for a long time. Different scientists have different views based on different assumptions about what the universe is like and what risks are acceptable. Some think the potential benefits of contact outweigh the risks. Others think the risks are too high, given our uncertainty. Both positions are reasonable given what we know, or rather, what we don't know. What seems clear is that this decision, whether to broadcast or stay quiet, is one that affects not just the current generation, but all future generations. If we attract hostile attention, if the dark forest hypothesis is correct and broadcasting brings predators, that's a mistake we can't undo. If we stay quiet and miss opportunities for contact with friendly civilizations, that's also a cost, though a more subtle one. These are the kinds of decisions we'll have to make as we become a truly technological civilization. Decisions with consequences that extend far into the future, affecting people who haven't been born yet. And we'll have to make them with incomplete information, with uncertainty about what's out there and what the consequences might be. This is part of growing up as a species. Children make decisions based on immediate consequences. Adults have to consider long-term effects, risks and benefits that won't be apparent for years or decades. A mature civilization has to think in centuries and millennia, considering consequences that won't be apparent for generations. Are we capable of that level of maturity? That's one of the central questions of the Fermi Paradox. Not just whether intelligence evolves, but whether intelligence can become wise, whether knowledge can be paired with judgment, whether technological power can be matched with restraint. The silence suggests that most civilizations can't make that transition. They develop technology faster than wisdom, power faster than restraint. They destroy themselves or trigger some catastrophe before they can spread to the stars. But maybe some make it. Maybe some civilizations navigate the dangerous period, develop the necessary wisdom, and survive to become something greater. Maybe they're out there, quiet and cautious, or transcended beyond our ability to detect, or waiting for us to prove we're ready before they reveal themselves. Or maybe we're first. Maybe we're the ones who will set the template, who will determine what a successful technological civilization looks like. Maybe billions of years from now, other species will study humanity the way we study the first civilizations on Earth, wondering how we managed to survive our technological adolescence, what decisions we made, what we got right, and what we got wrong. If intelligence is rare but not unique, then we have peers out there somewhere, but they're far away and hard to find. We're part of something larger, but still isolated. Children in a vast cosmos, knowing that somewhere others are asking the same questions, but unable to reach them, unable to share what we've learned or learn from them. If civilizations are short-lived, then we're in a race against time. Can we mature fast enough to survive our own technology? Can we develop the wisdom to match our power? Can we grow up as a species before we destroy ourselves? The silence suggests that most civilizations can't, that the filter is ahead and most fail, but maybe we can be the exception. If the galaxy is full of civilizations hiding from each other, then we need to be very careful about revealing ourselves. But we also need to think about whether hiding is the right strategy. Do we want to live in fear, in isolation, never knowing what's out there because we're too afraid to look? Or do we take the risk, reach out, hope that others share our curiosity and our desire for contact? If civilizations transcend or operate on levels we can't detect, then we're at the beginning of a journey that will take us to places we can't imagine, to modes of existence beyond our current comprehension. The universe might be full of intelligence, but we're not advanced enough to perceive it yet. Like children who don't know that radio waves exist because they haven't learned the physics. Each possibility demands different choices, different priorities, different strategies for the future. And we don't know which one is true. So we have to prepare for all of them, pursue the search while also working to solve our own problems. Reach for the stars while also taking care of our home. We keep searching, we keep looking up at the stars, we keep asking, where is everybody? And maybe someday we'll get an answer. But until then, we're left with the silence, the great silence, as some call it. 200 billion trillion stars, and not one confirmed signal. Billions of potentially habitable planets, and not one detected biosignature. 13.8 billion years of cosmic history, and no evidence that anyone else has ever asked the questions we're asking. It's the most profound mystery we've ever encountered, and it's not going away. Every year, we get better at searching. We scan more stars, study more planets, refine our instruments and methods. And every year, we find nothing. The silence deepens. At some point, absence of evidence starts to become evidence of absence. If the galaxy were full of broadcasting civilizations, we would have found them by now. We've looked at millions of stars. We've listened across billions of frequency channels. We've analyzed thousands of exoplanets. And we've found nothing. That has to mean something. Either life is rare, or intelligence is rare, or civilizations don't last, or they're hiding, or we're looking in the wrong way, or we're alone. One of these must be true. We just don't know which one yet. And maybe we won't know for a long time. Maybe not in our lifetimes. Maybe not for centuries. The universe is patient. It's been here for 13.8 billion years. It can wait. But we can't wait forever. Because if the great filter is ahead of us, if we're approaching the dangerous phase where most civilizations destroy themselves, then we don't have infinite time. We have to figure out how to survive our own technology. We have to develop the wisdom to match our power. We have to grow up as a species, and we have to do it fast. Because if we don't, we might become another mystery in cosmic history. Another civilization that asked, "Where is everybody?" and then went quiet before finding the answer. That would be the ultimate irony. We spend all this effort searching, wondering where they are, why we can't find them, and perhaps they were asking the same questions before their signals faded. I don't want that to be our story. I want us to be the exception, the ones who make it through, who solve our problems, who learn to work together, who spread to other worlds and carry consciousness with us into the galaxy, who become the ancient civilization that future species wonder about. The first ones, the ones who asked, "Where is everybody?" and then went out to find them or to become them. But wanting something doesn't make it true. We have to actually do it. We have to actually survive and thrive. And that requires work, wisdom, and cooperation on a scale we've never achieved before. But it's possible. And possibility is what drives us forward. The Fermi Paradox might not have an answer yet, but it has a challenge. Prove it wrong. Survive long enough to become one of the civilizations others wonder about. Last long enough to make contact or to become the first galaxy-spanning civilization in the Milky Way. Show that intelligence isn't inevitably self-destructive. Show that the filter can be passed. Show that someone, somewhere, can make it. Let it be us. Because if not us, then who? If not now, then when? The universe isn't going to hand us answers. We have to find them ourselves. We have to search the stars and study the planets, build the instruments and analyze the data. Keep looking even when we find nothing. Keep asking even when we get no reply. Keep hoping even in the face of the great silence. Because the alternative is to give up, to accept that we're alone, that we'll never know, that the questions don't matter. And I refuse to accept that. As long as we're here, as long as we can look up and wonder, we have to keep searching for evidence of life, for signs of intelligence, for answers to the oldest questions. Are we alone? Where is everybody? What's out there? And when we finally find out, whether the answer is we're alone or we're surrounded by others, whether we find friends or enemies or something we can't categorize, it will have been worth it. Because the search itself is what makes us human. The curiosity, the persistence, the refusal to accept ignorance when knowledge might be possible. That's who we are. We ask questions. We look for answers. We reach for the stars, even when they seem impossibly far away. And maybe someday, someone will reach back. Or maybe they won't. Maybe we'll search forever and find nothing but silence. But even then, we'll have learned something profound about the universe and our place in it. We'll know that intelligence is rare, possibly unique. We'll know that we're precious beyond measure. We'll know that everything depends on us, that we carry the only spark of consciousness in a vast, dark cosmos. And we'll have to decide what to do with that knowledge. Do we stay on Earth and risk everything on a single planet, or do we spread to the stars, ensuring that if something happens here, intelligence survives somewhere else? Do we protect what we have, or reach for what we might become? These are the questions facing our species in the next few centuries, and the Fermi Paradox haunts them all. Because somewhere out there, maybe, other species faced the same questions. Other civilizations stood at the same crossroads, and we don't know what they chose. We don't know if they survived. All we know is that we can't hear them. The galaxy is silent, and we're alone in the dark, calling out, hoping someone will answer, still waiting, still wondering, still searching for anybody out there who might be searching for us. 200 billion trillion stars, countless worlds, infinite possibilities, and as far as we can tell, just us. One species, one planet, one tiny blue dot in the cosmic ocean, looking up at the vastness and asking the simplest, most profound question in the universe. Where is everybody?